Next up, we have our next speaker. This will be Ryan Cao from Modulus Labs. Modulus Labs, like many of the projects you've heard from, is a graduate, or a completer at least, of the Stanford Blockchain Accelerator, led by Stanford alumni. I'll let them tell you what they're working on, since I would butcher it. But we're all very lucky to have Ryan come present. Ryan, come on up. Woo.
Hello everyone, I'm Ryan. I'm, as I've said, the CTO and co-founder of Modulus Labs, and I'm here to talk to y'all about an interesting little concept that we've been thinking about called commitments with qualia. So it's a pretty cool little statement. So the TLDR is that today I'll be telling you all about, first off, the situation. So what is going on in AI land? I'm going to throw you into a real life situation, and I want you to emotionally react to this. That is the whole point. We're then going to talk about kind of the problem with AI and what is going on. We're then going to talk about how to potentially kind of fix some of this stuff. So hint, hint, the issue is going to be, of course, robustness, explainability, kind of like the classic AI challenges. And finally, we're going to talk about how we should actually get there, how far it is, and why we at Modulus specifically have hope that we can get there. Okay, all of that was very abstract, so let's get into it. So what is the situation? All right. So let's say that you are visiting the doctor's office and this is your primary care physician. I generated this using Midjourney or something like that. But the point is that your physician comes up to you and says, hey, I have news and I have bad news. So the news is that I looked over all of your kind of medical scans and things like that. And the bad news is that you do have cancer. And so I'm going to have to diagnose you. And also I'm going to recommend that you start chemotherapy immediately so that the cancer doesn't get worse. Okay, this is a pretty kind of devastating thing to hear about. You're going to have to kind of consult with your friends and family. You're going to want to talk a lot more to your PCP about this. But let's say that it's not your human PCP who's doing this. Let's say that it's ChatGPT, or better yet, let's give them some credit. Let's say it's GPT-5 Medical who's doing this, right? So you see this interface, and you've been chatting with this chatbot, whatever it is, and it has told you that you have cancer and that you need to go do chemo. So I have a question for y'all.
Can you go say hi to the
How many of you would actually start chemo after this?
He's on your phone.
All right, we got a couple AI believers. That's good, that's good. I'm glad.
Last I checked.
As you should. Now, if you're anything like me, you might be asking yourself, oh, that doesn't feel quite right? Like, I should probably consult with a human. And so the question that I would like to pose is, what's the difference, right? What's the difference between this ChatGPT interface thing and the human physician, even if the AI model might be doing better than physicians in so many cases? Well, here are a couple differences that I can think of. So for one, I have no idea what GPT-5 Doctor was fine-tuned on or even trained on, right? Like, I have no idea what the data set is. Also, is GPT-5 Doctor even a certified medical professional, right? Like, I know the degrees that like my doctor has, but I have no idea what GPT-5 Doctor is doing. Also, are the reasons for this diagnosis that my doctor could explain to me, like, can ChatGPT-5 or can GPT-5 Doctor explain those reasons in a way which is actually sound in terms of medical reasoning? And finally, is it even the right version of GPT-5 Doctor which is running, right? How do I know I didn't get like a bad version of GPT-2 that's just like out here posing as a doctor? So there's so many kind of trust issues with this situation. And yeah, it's all just hidden behind this nice ChatGPT interface. Okay, so what's the problem with AI? Well, as we've kind of alluded to, there are basically quite a few issues with this situation, but maybe just to take a quick detour in terms of how I like to think about AI, this has been pretty helpful, but basically I like to think of AI as basically just creating algorithms implicitly using large amounts of data, right? So in other words, normally if I asked you to code a Python program, for example, which takes in an image of a dog or cat and then spits out whether it's supposed to be a dog or a cat, it would actually be pretty tricky to do this, right? Like, you would need to do like edge detection. You would try and figure out like, oh, do cats have like pointed ears and do dogs have floppy ears? Like, it would actually be pretty hard for you to do this. So in AI land, what we do is we say, okay, well, we're not smart enough to figure that out. So instead, we're going to just have this algorithm, have tons and tons of examples of cat and dog images, and just throw them at this model, have this basically learning algorithm until it's just good at recognizing those things, right? And so the end state of AI, as we are starting to see, is that basically AI allows us to kind of scale the recognition and the generation abilities of humans. So in other words, think about like the human professional and like all the training they need to go through and all the stuff that they're able to do that we want want to pay them salaries for. Now suddenly you can run this, but on computers, and scale it in these huge data centers like thousands or millions of times. So there's a couple other kind of like key things about AI, which I think are pretty important. One is that AI is kind of fundamentally very valuable, right? Because it's very hard to come up with these things ourselves. The data is very valuable. Additionally, AI results are becoming more and more sensitive, right? So sure, now things are like DALL-E, it's like, oh great, I generated my DALL-E image, that's so cute, like whatever. Or like Sora, it's like, cool, I generated this like random like a 1-minute video or whatever. But the point is that when AI is being used to give folks diagnoses, to like litigate these legal cases, to consult on things that are worth millions and millions of dollars, suddenly it's not really a laughing matter, right? You want to trust the model that you're actually running. The other thing about AI, though, is that kind of these security techniques that we normally use don't really work on AI. And by security techniques, I really mean zero-knowledge proofs. We'll get to that in a little bit, but fundamentally, AI is just very computationally expensive, and that makes it very hard to basically run these quality control things on them. Cool. So the TLDR is that AI currently is what I like to call unknowable. In other words, I don't know anything about it, right? I don't know if it's biased. I don't know if it's robust to adversarial attacks. Like, I don't even know if the AI model is the right one that's running. Additionally, AI is really unaccountable. In other words, even when I get a result from an AI model, I can't attribute it back to the model, right? There's no like link between the model and the actual like result that it's producing. And so, why should we live in a world like this? Like, this is not a great society. Okay, so what's missing? Well, first off, this is just kind of my list. Obviously, you can think of your own. But the point is that, first off, we're missing qualification, right? We need that degree. We're also missing kind of like the idea of explainability. Like, we want to know the logic behind these things. We're also missing kind of a guarantee of soberness, right? Like, you know that your doctor has like slept okay and that they're not drunk or high or whatever. And in this case, you want to know that no one has tampered with your AI model. And finally, you want accountability. You know who gave you the diagnosis, and you want to be able to potentially sue them for malpractice if needed. Okay, so now we're gonna take all of that framing, all of that framework, we're gonna put it aside real quick, and we're going to delve really quickly into the world of ZK proofs and zero-knowledge machine learning. So here we go, this is the solution. Okay, so real quick, at a very, very high level, a zero-knowledge proof is just a proof of correct computation. And so what that means is that if you and I agree on some function that I'm supposed to be running, then at the end of it, once I give you the result of this function, again, this can be a computer program, it can be a game, it can be an AI model, the point is that you can verify the proof that I'm sending you and know that I've done it correctly. So this is what we call compute integrity. Additionally, ZK proofs give us this idea of privacy in which you don't actually need to reveal some of the inputs to the computation that you're running. So in this case, if it's an AI model, you don't need to reveal the model weights. And so this happens to be very important, especially if you're trying to protect your own IP. Now, ZKML is literally just zero-knowledge proofs applied to machine learning algorithms, right? You just see machine learning algorithms as basically just a form of computation, and you just say, great, I'm just going to verify this computation using a ZK proof. The one thing that I feel like folks tend to miss with ZKML is this idea behind polynomial commitments. So real quick, the TLDR behind a polynomial commitment is that you basically have a bunch of data, and what you want to do is you want to use this, view this data basically as a polynomial, and then effectively hash the polynomial, but in a way to where you can evaluate it later at basically a single point. And there is some proof process that's necessary for this, but the point is that this commitment now allows us to basically put out there like just a pin for, sorry about the mic thing, but it basically allows us to just put out there like a pin for like every AI model and like every basically combination of model weights there is, right? So in other words, traditionally, ZKP says, I did this computation on these inputs and I got this result.
How's it going? Is that a hot mic? Yeah, that's a good question. I think they turn it down, but I should probably hand it to Avi.
Alrighty. Got some chitter chatter going on. Anyway, sorry about that, yeah. But the TLDR is that, like, traditionally we say, look, I did this computation correctly and I got this result, right? But in the case of ZKML, I would actually challenge you to think about it a little differently. Instead of saying, I did this computation correctly, I would really challenge you to think of the model commitment as almost a model resume in some sense. In other words, we have this basically thing out there which definitively represents the model, and now every single claim, every single statement that we want to make about the model, including a statement such as, it's not robust, it's past the MCAT, all of those things can now be layered on top of this basically commitment. So for example, the name of the model, right? GPT-5 medical. But also, we might want qualifications. Qualifications such as, oh, I got a 522 on the MCAT, or I got a 260 on the step 2. I had to look up the range of the step 2, so yeah, it's pretty good, I think. Additionally, you might also want to, for example, have explainability. You might want to know, like, sorry, that's the last one, yeah. But yeah, point is, additionally, you might want to have basically a history of like diagnoses, right? So other folks who have been diagnosed with this model previously can basically layer their statements now on top of the model and say, hey, look, in aggregate, of all the 1,310 ontology diagnoses that this model has made previously, it's gotten 1,260 of them correct. And so I should trust this model more because it's done so many correct diagnoses. And finally, maybe you want some explainability. So where is the source for basically the symptoms to diagnosis coming from, right? And maybe it's coming from this like nice textbook of medicine, which again, I also just Googled, so I have no idea if this is credible or not. But yeah, the point is that all of these things are what we call commitments with qualia. So in other words, you have a commitment which basically pins the model down, and then each of those statements that you just saw, those can all be formulated as statements of computation. In other words, you can basically create a ZK snark or a zero-knowledge proof of all of those things and just attest it to the model. And the point behind the ZK snark and the commitment is that the only way that these snarks or these statements can be correct is if the commitment verifies them. And that is why the commitment is so fundamentally important to all of this. It is the thing that grounds all of these statements and says that all of these statements have to be done over the same model. And so we just feel like this is very, very powerful. Other statements you can prove, for example, this model is robust against adversarial attacks of X nature. So if I want like a fast sign gradient method or something like that, it's robust to that. It gets 98% on that data set. Conversely, you might want to say something negative about the model. So you might say, look, provably, this model generates a watermarked image. So clearly there's some shady shenanigans going on with the training, but the point is that when you feed it a latent seed within like some subspace, some vector subspace, it generates a watermarked image. And so this model might not be so good, could be grounds for suing, right? Okay. So the TLDR is that zero-knowledge proofs basically allow us to endow models with qualia, so all of these kind of properties, and also provenance. In other words, when you get a result from this model, now you can also trace it back to the commitment to that model. Okay. So that is kind of I guess like the snark stuff. Okay, so how do we actually get there and why should we have hope? Okay, here we go. So in terms of this quality control for models, actually this has already been happening a little bit in kind of the Web 2 space. In other words, there are these centralized kind of trusted authorities. So if you think about, I think last year, Scale had this like partnership with basically the government in which they said, look, we will do model labeling for you, right? Like we will attest to the fact that these models are robust, secure, whatever. But we don't actually want that. We don't want folks like Scale to just be able to kind of like label these models arbitrarily and not tell the rest of us how they're testing them, or it's just like oh, just trust me, bro, like I got it, right? So instead, what we really want is to do this via math, via practical ZKML, right? Like this is really the way to do this. And we want all these things to settle on chain because that is the most neutral kind of settlement layer, right? Put the commitments on chain, layer all of the qualia on top of those commitments, and everyone gets to verify every single statement. Okay, so are we there yet? Well, no, because if we were, I probably wouldn't be talking to you about this. Let's just take an example. So there's this model called GPT-2 XL. It has 1.5 billion parameters. Just for fun, we at the Modulus team decided to basically snark this in a what we call a generic proving system, and it was atrocious. So on a generic ZK prover, I'm not going to point fingers, but I will name names. It's Halo 2. The total prove time was 322,000 seconds. That is over 80 hours of proving on a 128 core machine with 1 terabyte of RAM. This makes no sense. There are also some metrics for other things you might need to do in Halo 2. For example, store over 30 terabytes of this like prover key thing. Yeah, it just doesn't make any sense. Also, all of this is without recursion. We needed to break GPT-2 up into basically a bunch of blocks, and then we need to break each of the decoder blocks into 3 separate sub-blocks and prove each separate sub-block. So we end up with like 144 different snarks, and we need to recurse, so on and so forth. Yeah. In other words, this is just like the bare lower bound for that. Okay, so Now I'm going to introduce y'all real quick to the concept of kind of like specialized versus generic provers and just take a look at the overhead. So sorry for the jank graph, I just drew this last night. But the TLDR is we have kind of like the technique, so what we're doing on the x-axis, and then we have the overhead. In other words, how much longer does it take to prove than it takes to compute the same thing on the y-axis. As we'll see, even though it's a log scale, there is a big, giant thing with the gap in between. And the TLDR is that Halo 2 gets something on the order of basically 300,000x overhead. So for every second of compute you do, it takes 300,000 seconds to prove that same compute. Now, if we're going to talk about the specialized regime, actually we at Modulus launched, or rather, I guess we've been building this prover system called Remainder. We wrote a paper on it that we released on Monday. And for a certain class of AI models, we actually see just 180x overhead. So the difference between these two is that Remainder uses a proving system called GKR. If you're interested, you can talk to me about it afterwards. But the TLDR is that GKR is just much, much, much better at machine learning algorithms than something like Halo 2. There are other sort of data points from the literature. There's this 2021 paper called ZKCNN. It also used a form of GKR to basically do verifiable inference. I think 90x is actually not giving enough credit. It does better than that. Also, in Justin Thaler's 2013 paper, he did basically a couple of experiments on proving basically what we call the distinct problem, in which you take a stream of elements and you count how many distinct elements there are, as well as basically a native matrix multiplication basically protocol, and we see respectively 10x and 6x kind of overheads for this. So I'm just going to draw the trend line for you. Yeah, obviously you could have interpolated that. And the question is like, okay, where do we need to go, right? And so I think we really need to go to basically this 10x mark. And the reason for this is that currently it takes Llama 7 billion about basically 0.1 seconds to do inference on a single token. And so currently, again, Modulus has about 200x, but the point is that if we get to this target overhead of 10x, then we basically get 1 second per token of provable inference outputs. And really, we can do this commitments with quality at scale, right? All of these models can now have all of these attestations over them, and you know what you're getting. And you're basically looking almost another like person in the eye and saying, great, I know all of your credentials. I know what you're on about. Let's do this. Okay, thank you so much for coming. This is our Twitter.
All right, thank you, Ryan. Well done, sir. And I won't take the QR codes down before everyone's had a chance to get them. I'm looking at you, Matt. Okay.